do that unless there happens to be time left at the end, which I really doubt. And then I may come back and show you a little bit more about how one actually derives the basis. But at one loop, and again, we're working, just to make things easier conceptually, we're working entirely a massless theory. So all the internal lines in these integrals are massless. We have a variety of boxes, and we're going to consider the sort of general case where we have at least 5 legs on the original amplitude. We have a variety of boxes, and I think the notation should be self-evident, but I'll explain it in a minute. Anyway. So we have 1 mass boxes, so-called easy 2 mass boxes, hard 2 mass boxes, 3 mass boxes, and 4 mass boxes. So we're working in a context where all the particles are massless, so the internal lines are massless. But when we do integral reductions, of course, we can end up with arguments to each of these integrals that are sums of the original momenta in the problem, and that's what I'm denoting here by these multiple lines. So these legs can be mass at 4. There can be single lines left over. These are single massless momenta that were original arguments for amplitude. They can also end up as arguments to the integral functions, and that's denoted here by single lines. So we can have a variety of patterns. These are actually all the patterns of masses we can have for the boxes. I think better to turn off the screen. Sorry. There we go. Similarly, there's 3 kinds of triangles we can have. 1 mass triangles, 2 mass triangles, and 3 mass triangles. And finally, there can be bubbles. Here there's no choice. The bubble always has a massive external leg. Does anyone know why? The question is, why do we not have massless bubbles in dimensional regularization here? So let's actually just take a quick look at one of these integrals, which is the lucky will appear right over here. So this is the so-called easy 2 mass box. It's called easy for historical reasons because you can actually derive a Feynman factorization which can be integrated to all orders in epsilon very easily. That's not true for the hard 2 mass box. Let's see here, where is the eraser pointer? So this is integrated in dimensional regularization. So 4 minus 2 epsilon dimensions. There's 4 propagators. And as I say, the way that you can do this is simply to do a Feynman factorization. You do a clever one, actually, where you combine opposite lines first and then combine the results. And that gives you an expression you can integrate in terms of hypergeometric functions. And if you then expand that in epsilon, you discover that you have the leading term is a 1 over epsilon squared, or at least it appears to be a 1 over epsilon squared. 1 over epsilon squared in the virtual corrections is coming from an overlap of soft and collinear singularities. The collinear singularities, remember thinking back to the first lecture where we saw them in the real emission context. In the virtual context, they appear as poles in epsilon. Likewise, for the soft singularities, and in principle, when they overlap, you can get a 1 over epsilon squared, and that's a generic feature of gauge theory. At every order in perturbation theory, the leading singularities will have an additional power of 1 over epsilon squared. And I say appears to because actually in this particular integral, if you start expanding these objects in epsilon, you'll see that as 1 plus 1 minus 1 minus 1. So, in fact, the leading singularity cancels. And that's not actually all that surprising. If we had a little bit more time, we would go through it. So, in fact, the leading singularity here is going to be a logarithm of, let's say, s over n2 squared divided by epsilon. That's really just a collinear logarithm. In addition to logarithms, which are functions that I expect most people here have known since childhood, there's also dialogues. Does everyone here know what a dialogue is? Who does know what a dialogue is? Who doesn't know what a dialogue is? Okay. So learn to like polylogarithms. Dialogues are the simplest of these functions. These are essentially iterated logarithmic integrals. So it's a logarithm you get by just doing a dt over t integral. Then, well, in that case, you want to go from x to 1. But here, if you essentially iterate that integral, then you'll get a dialogue. And if you iterate it further, you get trilog, echolog, and so on and so forth. And you can also get more generalized ones, which I won't show you here, where there are multiple arguments. And in a sense, you're doing integrals in multiple directions. So there's a variety of dialogues. The other thing, the feature that's worth pointing out is that there's this kind of strange looking denominator. And this is not a pole. So you're wondering, maybe, what is this object doing here? After all, at tree level, we expect only poles to show up as singularities. And okay, loop level, maybe things are a little bit different. They're branch paths and so on and so forth. But this appears to be a new kind of singularity. In fact, it's not really there. And you can see, for example, one of the things about the dialogue is that you can see if I take x to 0, here dialogue of 0 is 0. And you'll notice that if I combine terms here, that the numerator is exactly what appears in the denominator here. So this dialogue vanishes when this vanishes. So in fact, in this term, for example, that singularity is spurious. And you can use dialogue identities to show that it's also spurious elsewhere. So in fact, the term inside braces, actually ordered by ordering 1 over epsilon squared, will vanish when this object vanishes. So this is an example of a spurious singularity. It seems to be there, but it's not actually there when you expand it. And life is full of these things. And sometimes the cancellations can be more intricate across different integrals. Okay, so I think that's all we really have to do. Oh, I'm sorry. So this is the easy two-mass box. And if we look after the picture, then actually I've drawn it here with M1 and M3, but if we label 1, 2, 3, 4, then M2 and M4 are simply the masses of the two massive legs in this box. So this is that clear? Let me label it explicitly here. 1, 2, 3, 4. So again, 1 and 3 are massless legs, and 2 and 4 are massive legs. So N2 squared is simply the...
Yeah, of course. It can be expressed in terms of the K1 and K1 to K1 to 3 that 0 is the left.
Yeah, so for example, in this case, M2 squared is simply equal to K2 squared, and M4 squared is simply equal to K4 squared, which is equal to K1, 2, 3 squared. Let's go down. Okay, so that's the set of integrals we have. And our goal is to identify the coefficients of each of these integrals. What we were able to do last time is we looked at a certain cut where we're isolating, consisting of these two propagators there. And of course, those two propagators, there could be a variety of boxes. I could shift legs from here to here. So some of these boxes will show up, some of these boxes. In addition, some triangles will show up and some bubbles as well. On the other hand, there will be some integrals that, for example, can't show up. So I'll be picking out a subset of them, and then I'm doing the reduction algebra that would be analogous to the kind of tensor reduction that you do if you're doing Feynman diagrams in order to isolate the coefficients of each of the integrals. Now, today we want to go beyond that. First, though, we should just think a little bit about the roles of dimensional regularization. And this is, again, more of a kind of a conceptual understanding. So the claim is that working in dimensional regularization, we'll really be able to extract the entire amplitude. And it's essentially a very sophisticated way of doing dispersion relations. It's true that I'm not actually doing a dispersion integral explicitly, but implicitly I'm going from a phase space integral to a loop integral. And if you think back to the original version 0 of the unitarity method, then there was this subtraction constant. And that subtraction constant was associated with the fact that there's bad ultraviolet behavior, there's an ultraviolet divergence in the object that we're trying to integrate. So the first thing that dimensional regularization is doing for us is it's acting as a UV regulator. And in the standard fashion in field theory. So once you work in dimensional regularization, there aren't any ultraviolet divergences. You're trading them in some sense repulsion. Epsilon, but as long as epsilon is non-zero, it is actually a large but a finite number. The thing that's actually more important from a practical point of view when we're doing these calculations in the QCD, we've seen an example of that already in this easy two-mass box. The easy two-mass box, you can convince yourself very quickly by power counting, is ultraviolet finite. And yet there's still singularities in epsilon. Those singularities are infrared, as I explained. They have to do with the Pfropst and collinear structure. So it's acting as an infrared regulator. And we're going to be using dimensional regularization for the singular terms in real emission. That would be a separate set of lectures, but we've seen a little bit of a flavor of that in the first lecture. And it's also acting as an infrared regulator in the virtual corrections. And all these integrals are going to, in general, have poles in epsilon. These guys have just 1 over epsilon. This one is actually finite. And these two integrals have a genuine 1 over epsilon squared. The same is true over here. There's a 1 over epsilon squared. This is 1 over epsilon, and this one is finite. And this one has an ultraviolet 1 over epsilon. In fact, that's the only source of ultraviolet 1 over epsilon in one loop. In the context of unitarity, there's actually a third role that dimensional regularization is playing, and it's linked to its role as an ultraviolet regulator. So what it does is it removes the ultraviolet divergence. So the integrals become convergent. And as a result, there's no subtraction ambiguity in dispersion relations. So at least conceptually, that's the reason that we're able to reconstruct the entire amplitude, is that the issues that we would otherwise have are taken away by dimensional regularization. Now, there's also a slightly more down-to-earth way of looking at that. If you remember again, the version 0, in some sense, of unitarity was going from a branch cut to a logarithm. So reconstructing a dispersive part from an absorptive part. And Well, the integrals are fine. All these integrals have branch cuts, and so we can see once we remove the subtraction ambiguity how it is we'll be able to uniquely reconstruct the logarithm in a sense, or the dilogarithm from branch cuts. But what about those rational terms? Rational terms clearly don't have branch cuts. How am I getting a handle on those? And we're not going to have time, I think, to see that explicitly, but if you do unitarity in 4 minus epsilon dimensions, you can certainly get at those. And the answer is that when we're working in dimensional regularization, of course, we have to change the dimension of the coupling. We're shifting slightly away from 4 dimensions. And what implements that shift in the coupling is that there's always some power, some invariant to the minus epsilon that comes in front. So whatever the amplitude was, whatever the expression was in 4 dimensions, there's going to be an additional factor of minus s to the epsilon in front. And of course, that factor is not going to be inert. It's going to give rise to a variety of logarithms, which are then also important in terms of scale running and things like that. So when we now expand, so if we have a rational term now, it's really secretly multiplied by minus s to the epsilon. And you say, so what? There's no poles here, and I'm going to take epsilon to 0, and so then this just disappears, and I'm left with my rational term. But if we're working in 4 minus 2 epsilon dimensions, in a sense, we're working to higher order in epsilon, and at that order in epsilon, all of a sudden, lo and behold, we now have a logarithm. So by taking one higher order in epsilon, we all of a sudden have a branch cut. We can reconstruct this complete object, including its rational prefactor, and we then realize that this is really reconstructing minus s to the epsilon. We take epsilon to 0, we're left with a rational term that's we're interested in. So that's the role of dimensional regularization. And so we now want to move on from unitarity to generalized unitarity. So far we've been picking out contributions with 2 propagators. We've been insisting that there be 2 propagators in every contribution. You might wonder, why not insist on more? Can we cut more lines? Instead of just cutting 2 lines, can we, for example, cut 3 lines? So that would be our ordinary unitarity cut. Now let's cut a 3rd line. Well, what would be the advantage of that? Well, one advantage is very clear. If you cut 3 lines, you can't have any bubbles, so you don't have to worry about removing the bubble in that channel. Moreover, once you cut 3 lines, instead of having multiple triangles, so having, let's say, some combination of 1 and 2 matched triangles, you'll only have a single triangle. You'll still have boxes, but there'll be fewer of them because there's fewer boxes that share 3 propagators compared to just 2 propagators. And do we have enough degrees of freedom? Well, we're essentially, as far as the cutting is concerned, so that if you think back to how we were doing things yesterday, then the algebra and the structure of the propagators were treating in 4 dimensions. The loop integral we're then doing in 4 minus 2 epsilon dimensions. So in 4 dimensions at one loop, we have 4 degrees of freedom. There's 4 components. There's 4 components of the loop momentum. The loop momentum L. So in fact, we can imagine not just cutting 3, but even 4 propagators. And that would be very nice, because then, in fact, if we were able to do that, we would have no triangles at all. We just have boxes. And in fact, we have a unique box, because there's only one box that has 4. Taking the loop integral into 4 minus 2 epsilon dimensions, we can control all of that. So we have, write down our box integral. And again, just as a notational device, let me remind you that ki dot j is just the sum of momenta from I to j. So k12 is k1 plus k2, for example. Okay, so we saw last time how we do cuts. We replace propagators by delta functions. So let me do that. And let me be a little bit sloppy about factors of I and 2 pi to the 4th. Just cross that out and really just focus on the delta functions themselves. So we know about delta functions that what they're trying to do is they're trying to localize the integral we have for, so the integral over a delta function is going to constrain each of the components to solve the equation. We have 4 delta functions, so there's 4 simultaneous equations that we need to solve. Yes.
Last thing for the positive energy.
The plus is I'm just copying what we did last time. Yes, it means the positive energy. And if you're a little bit puzzled by that, then just hold that thought for a few minutes. We learned how to do a cut, and I'm just blindly applying that idea to extending from 2 to 4 cuts. So the question is, how many solutions do we have? We have 4 quadratic equations that we need to solve. And it turns out that the counting solutions of multivariate polynomial, higher degree polynomial equations is actually a fairly non-trivial thing to do. But here we can observe that we can take linear combinations of these equations. For example, we can subtract this one from this one. That's going to leave us with an equation that's only linear in the loop momentum. And likewise, we can subtract the original form of the second equation from this one, and that will give us L.K2, S12 minus K2 squared equals 0. And again, here we can use momentum conservation and then subtract the very first equation, and we then have 3 linear equations and 1 quadratic equation, and in this case it is easy to count. We expect 2 solutions. Let's actually solve these equations. Let's do it explicitly. And let's do it explicitly in the case that legs 1 and 4 are massless. So we know that L is going to have to be a massless vector, so we can write down the general form of a vector like that. Let's see here. So we can use our spinner to write down a null vector. And this is a nice choice because, of course, the first equation, the vector is null, so it's automatically satisfied. If we got it into K1, and then you see we're going to get an angle product of 1 with 1, so that'll automatically be satisfied. If we got it into 4, then we're going to get a bracket product of 4 with 4, so that's automatically going to be satisfied. And we have one more equation that we can impose. It's the third equation, and when we impose that equation, we'll find that S12 is equal to C over 2 times 1 to 4. So we can then solve for C. If leg 2 happens to be massless as well, then we can further simplify this result by dividing out by the angle product of 1, 2 on both sides, but that doesn't really matter. In any event, we have a solution for C. And we would find that our vector is, let me write it in the form such that, so we have S12 divided by 1, 2, 1, 2, 4 times 1 is 4. And similarly, there's also going to be another solution which is given by minus S12 over 2, 4, 2, 1 times 4 is 1. So we have our 2 solutions. Okay, so I've got K2 into here. That gives me 1, 2, 4, and that thing is supposed to be equal to S12. And that's what fixes the normalization C. So we have 2 solutions, but there's a problem. The problem is that, of course, vectors 1 and 4, and therefore spinors 1 and 4, they're completely unrelated. They're certainly not complex conjugates of each other. That means that these solutions are complex. But the domain of integration here, to ignore the Feynman iapsilon for a second, the domain of integration here is the real slice. The components of L are real. And if we think about defining a delta function as some delta convergent sequence of Gaussians or Lorentz or 1 over x squared plus a squared type functions, then if we plug in a complex value here, whatever the way we define the delta function, we're going to get 0. In fact, the notion of a positive energy, I mean, what is a positive energy when the energy is complex? It doesn't mean anything. So we have our two solutions all right, but they don't lie in the domain of integration of the delta function. And so this quadruple cut is going to give us 0. And ultimately, if we were to apply it to the other side of the equation, we also get 0. So we would derive a true equation, but one that is not very useful.